recording started, and we can start the show. So first order of business to go over the answers for the formative assessment number 5. This is a bit of a throwback. So there's a few questions on here that are things that we introduced earlier in the semester but have continued to utilize. And so I wanted to make sure that some of the old stuff didn't escape as we're adding new things at the same time, since it's all sort of cumulative in nature. First question, in what situations, what types of predictors or their relationship would a Pearson correlation be sufficient to describe the bivariate relationship, and in what situations would you need a model? So a few of you talked about when you're looking at multiple predictors and trying to ascertain unique effects, that wasn't the answer to the question. So in the situation where you're just trying to get a bivariate relationship, meaning the relationship of one x with one y, when can you do that with just a Pearson correlation, and when do you need a model? What do you guys think? One fixed slope is one vote. So if you have one fixed slope, do you need a model? Nope. Pearson correlation would work just fine for that. So if you have a linear relationship between a quantitative x and a quantitative y, or you have a binary x with a quantitative y, a Pearson correlation will cover either of those two situations just fine. The r that you would get if you square it would be your model r square. The t-test statistic that gives you the significance of the correlation. If you square that, it would be the f for the r square of the model. So it's a one-to-one correspondence there. When would you need a model then? Watching the chat window, we've got one answer. Who else wants to play? We have still talking about bivariate relationships, and so multiple predictors are not yet relevant, but more than one slope is an answer. When would I need more than one slope to describe the effect of a variable? Like what kinds of variables would need more than one slope? Like in homework 4 that just finished. Each of those models had more than one slope in it, right? What were those situations? Got either multi-category. Yeah, so the golfing groups, we had 4 groups which took 3 slopes to describe their effect. So more generally, if you have a categorical predictor that has more than 2 groups, you need more than one slope. And so you need a model to be able to describe each of the group means and the differences between the means as your bivariate relationship between the grouping x and the quantitative y. Nonlinear effects, right? Like the nonlinear effect of enthusiasm or piecewise experience or education. So if a quantitative variable needs to be described by something other than a straight line, either a bendy line or multiple sections of a line somehow, that takes multiple slopes to do that as well. Non-bivariate variables, maybe. What do you mean by that? Waiting for a clarification on that one. Trying to think of other variable names. If you mean like non-binary, I'll take that. That's what I would call categorical. If you have a variable that is categories, those categories could be ordered, which is known as an ordinal variable, or they could be unordered, which is known as nominal. But yep, I'll take that. So anytime basically the effect of a predictor on an outcome takes more than one slope to describe it, that takes a model to be able to flesh all of that out rather than just a Pearson correlation or a simple any sort of yeah, we'll leave it at that. Just one correlation would not be sufficient. Okay, so questions on any of those ideas? So where those, I'm going to point to where those things were in the lecture slides. This is the last slide of lecture 3, where I was saying foreshadowing. So this was the transition between putting one slope in a model at a time and putting more than one slope in a model at a time. So this is the usage that we just talked about, the idea that you have a predictor variable that takes more than one slope. And these are the other situations in which we would need a model, but they extend beyond just bivariate into bivariate versus unique. So that's slide 32 of lecture 3 that I'm looking at here for that. I also pulled up, let me see, this one. This is slide 42 of lecture 4, which echoes the same conclusions. So when you would need a model to describe a bivariate relationship, anytime your predictor takes more than one slope, more generally, whether it's nonlinear relationships or grouping variables, what have you. Okay, does that make sense? Because your faces don't look happy, I gotta tell you. The faces that I can see right now are not looking happy. So then it's like, what did I do? Or is it just like, it's a bad day, or you're hungry and you haven't had lunch yet, right? There's lots of reasons for that. Are we okay? Okay, faces I can't see, are we okay? Yellow thumbs? Okay. It's a bad semester, yes. Yes, but stats is hard. Yes, also true. Some people were up late, too late last night. Yes, I noticed. I look at the time when things are submitted and I'm like, 2:47 in the morning. I have not seen that time in a very long time. So yes. Okay, so it's not me then, right? I can relax. Think I haven't done something wrong. If teaching stats is wrong, I don't want to be right. Somebody's got to do this job. Teaching statistics is one of those jobs where when you're trying to make small talk with other people and they ask what you do for a living, it immediately inspires a response that's something like, "Oh, I had to take statistics and I hated it." Like, "Oh, well, where do you go with that?" "I'm sorry. My goal is to make you hate it less than you might otherwise." How's that? It's important to be clear about one's expectations. You might eventually grow to like it in spite of yourself. And if you do, then that's great because there are so many people who don't want to do this that you will always have a job. So, yes, stats is hard, but it's worth it. It is worth it indeed. There's plenty of jobs that other people have that I think to myself, oh, I would never want to do that. Right? Different strokes for different folks. Anywho, changing gears then. R square. So this one I realized could have been worded a little bit more definitively based on the answers that I got back. Several folks told me things that were true about R squared that I hadn't anticipated. So what do you think of when you think of R square? We'll do like a free association thing here. What words or pictures come to your head? Proportion to variance, yeah. So how much of the variability in your outcome has been explained or accounted for or is attributable to your predictors? All of those words are synonyms. That's the big one. How much information do you have some ability to predict based on your predictors and versus how much is left over? R square is a proportion. So what is the worst that R square could be? This is a finger question. 0. Yeah. So when would you see a 0 R square? I can think of 2 situations. If you put a predictor in that has no effect or is unrelated or has no relationship, yep, that's a good one. That was one of the instances that I was thinking of. The other is if you have an empty model. If you literally have no predictors in the model, then your model has not explained anything. So if all the variance is yet to be explained, then you have an R-square of 0. And that can happen if you haven't tried to explain it yet, or if you've tried and failed. So if you put in a predictor whose slope is 0, for instance. Yes. So that's one way to think of it, is as the proportion of variability in the outcome that has been explained by the predictors. The other is as R, as a correlation squared. And this one not many folks mentioned. If you think about how the model creates an expected outcome for each person, what's that called? Like if I take the intercept plus the slope times my value on this x predictor plus the slope times my value on the next x predictor, and I put it all together and I create a predicted outcome, what is that called? Looking through my chat, y hat, yeah. Expected outcome, predicted outcome, conditional mean, y hat, any of those terms will describe it. So R square is the square of the correlation between y hat and y. So if I take my model and I create a predicted outcome for each person based on their predictor values, that's y hat. In the data set, I have their original y. So I could make a new column that's y hat based on my model. And software will do this for you, by the way. This is one line of code. You don't have to do that yourself. And I can correlate my predicted y hat column with my real y column. If I take that R correlation and square it, that's R square. So it's literally a measure of how good your model predicts your outcome. We put it in a squared metric so that slopes that are positive and negative don't cancel each other out. So the worst it can be is 0, the best it can be is 1. Let me make sure that I haven't missed anything on the things that have gone by. I think we're good. Okay, does that much make sense?
A quick clarification, Lisa.
Okay.
The R squared of the model and the R squared you were describing between Y and Y hat, are those the same R? Or
Yes.
R squared? Okay.
Yes.
Thank
Yes.
you.
The correlation between y and y hat would be r. You'd have to square it to make it r square. But it is the same r. And for whatever reason, when you talk about r, people use a lowercase r, but then when you talk about r square, it switches to uppercase. I have no idea why, but that's just a thing. So it is the same r.
Perfect. Thank you.
Thank you for the question. The other thing folks told me about is unique and common variance with respect to this. R square is a measure of what each predictor contributes uniquely and what they have in common. So if I go to, let me find the picture that I wanted, this picture. So this is slide 12 in lecture 5, the Venn diagram or the Ballantine image. The idea behind this picture is that x1 and x2 both are related to y. The sum total of how x1 relates to y is area A and area C. And the sum total of how x2 relates to y is area B and area C. But C, because it's in common, neither of these variables is going to get credit for, but it will contribute to the R square. So the R squared does reflect the joint contribution that no variable gets credit for, as well as the unique contribution that each variable brings by itself. And if you would prefer talking about the cast of This Is Us instead, here's the slide that goes with that. The idea that R square is like how many rooms in the house got clean, and that's a sum of each of the rooms that one person cleaned by themselves, their unique contribution, plus the rooms that more than one people claimed they clean. So because they still got clean, even if we don't know who did it, right? It still counts in terms of the total effect of the people working or the model predictors in this case. Okay, does that make sense? Okay, Tasha likes the examples. Thumbs up. Yes, I like talking about TV because there's not a lot of things that I have left during the pandemic to entertain myself, right? But TV is always there for me. And Grey's Anatomy came back. It's back. And I don't want to spoil it, but the ending was a shocker. So it's worth hanging in there for the full 2 hours or an hour and 20 minutes if you can skip the commercials to see what happens. But this actually sets up is it the last question? Is it the next question? Yes, the next question. I thought so. In what situations would you expect a predictor's unique contribution to differ from their bivariate contribution? And this is something that not many folks gave me the answer that I was looking for, so I realized I need to go back over it. So this is helpful. The quizzes are helpful from both sides of this, at least. The intention is things that I see multiple people not commenting on means my bad. I should have made more of an effort to emphasize that. It's also hopefully helpful for you to try and emphasize what are the big picture ideas that you need to review. But when would you have a situation where the number of rooms cleaned is the total number of rooms that people actually cleaned? It has to do with overlap. So like if I go through all of the X's in here, how many X's are in this picture is more than the 9 possible rooms because there's overlap. So the number of rooms that each person cleaned independently is going to differ than the number of total rooms that they claim they cleaned if there's overlap. And so the way this translates into models is that if two predictors are uncorrelated, then their bivariate contribution is going to be the same as their unique contribution. So going back to my picture here, if X1 and X2 had no overlap whatsoever, if they were like separate non-overlapping circles, then the effect that they would each have in the model would be the same regardless of whether the other one is there. So overlap. If predictors overlap, then the story changes when you put them together in the same model versus when you're looking at them in separate models. And it can change in somewhat unpredictable ways sometimes, which is why just having a bivariate relationship is not necessarily a precursor to looking at its relationship in a multivariate sense, meaning all together. Okay, does that make sense? Questions or things that you want to hear more about with that? Okay. So it's pretty rare in practice that you would have predictors that are uncorrelated with each other. The only instance that I can think of when that would happen is when your predictors are manipulated group assignments, like you're doing a true experiment and you're telling people, okay, you go in this condition and you go in that condition. And of the people in each condition, you subdivide them into one group versus the other group. So if you have like a 2x2 kind of design where there's two sets of grouping variables and you've allocated people to groups such that they're equitably distributed, then the predictors that would go along with those two groups would be unrelated. And so you have the best chance of detecting each of their effects because they're not in competition with each other. Question, what about suppression? We haven't talked about that yet. I've got a slide on that. Suppression means that a predictor's unique effect is larger than its bivariate effect. And that tends to happen most often in practice when predictors have a negative correlation with each other. So there's particular mathematical conditions under which it happens. But that's one of those things where a predictor looks more important than you would think it should after putting other predictors in the model that don't compete with it. They suppress irrelevant variance. So, point being, you can't always predict what's going to happen when you put everything together based on how they act separately because of the way that predictors are related to each other. Okay, so questions? No? All right. Last one. The relationship between effect size, statistical significance against a null hypothesis of 0, and sample size. I made you guys a picture. I put it up on the website for today, and I thought it might help because as I was looking all of these things over, a picture came into my head, and whenever that happens, I have to make one. So let me find the picture that I made and put it up. So here's the picture that I had. If we form this sort of continuum of effect size, so think of this as an axis where the left-hand side is no effect whatsoever. So a predictor is not related to an outcome, for instance. The strength of its relationship can be described as how far over on this line you've gotten to, up until the end where you would have, say, the strongest possible effect. And I'm being deliberately vague because what strongest could possibly be depends on what your measure of effect size is. If you're in a correlation metric of effect size, so if you hear R or R square or eta, by the way, eta is an R metric, then the most that it could be is a correlation of 1. In contrast, if you're in a mean difference metric, like Cohen's d or any of the associated standardized mean differences, the highest those could be is infinity. You can have a mean difference that's as large as it could possibly be. So there's no cap on that. So just picture this as sort of the strongest. At a given effect size, the role of the significance test is to make a cut and dry decision, basically, as to whether or not we think that that effect came from a distribution where the population came from a population distribution where the null hypothesis is whatever you said it was. So in most cases, we're going to say that it's no effect is the null hypothesis. So how likely is it that the effect that we found came from a population distribution with the null hypothesis? And if it's sufficiently unlikely, we draw a line in the sand. So this is me literally drawing a line here. And at a given effect size, we would make a decision that any effect smaller than that would be not significant, and any effect larger than that would be significant. And where this line in the sand gets drawn is a function of sample size. At a larger sample size, the blue line moves to the left. And at a higher sample size, or a smaller sample size rather, it moves to the right. At a larger sample size, it takes less of an effect to get yourself over into significant territory. And at a smaller sample size, it takes more of an effect. So the reason effect size is so important is that if you read in a paper, say, that a result is significant, that could mean that you have a strong effect or that you have a large sample. Because a given test statistic, like our friends T and F, are a function of sample size and effect size. So having a large sample doesn't necessarily mean that you're going to get a stronger effect size. It means that the effect size that you found is going to be more likely to be significant, to be unlikely to be part of a distribution that's centered at 0, because with larger samples, the effect size that you get across repeated samples is less wiggly. So larger samples improve precision, which makes it easier to move away from the null hypothesis and to have the separation of the null hypothesis distribution and the alternative hypothesis distribution. So power is your chances of finding an effect. What that means is finding it to be not 0. So the 3 things that improve power is more people, larger effect size, and a larger willingness to be wrong with a false positive, larger alpha, type 1 error rate. So bottom line, when you're reporting things, we want to report whatever the effect is that we found from the model, like the slope estimate that we got, the standard error that describes how wiggly it would be across repeated samples, the test statistic that's created from the combination of those two things, the p-value that goes with it, and the effect size then that quantifies in an absolute sense how strong the relationship is, irregardless of significance. Did you know that's a word now? Irregardless. It was accepted in the dictionary. And I say it when I really want to make the point. Not just regardless, but irregardless of significance. So effect size has nothing to do with significance, or has nothing to do with sample size per se, other than larger samples make effects more consistent across samples, less wiggly, smaller standard error. Okay, I don't know if this helps, but I thought I'd throw it out there. So questions, comments, clarifications on effect size versus significance versus sample size. It helps. Can you please upload this? I did. This slide is on the website for today. At least it should be. I can double check that, but I thought I put it up this morning. Did you? Okay, you found it? Okay. Yes. Yeah, I always try to put up things that I make on the fly, but this keeps it spontaneous. Okay. Questions on any of that? All right, well, just now I made something else that I wanted to go over to clarify R-square and semi-partial correlation squared, changes in R-square, and all of that stuff. So let me find what I was typing in here. I made up a little Excel sheet. Okay, so I just made up some numbers. This is just to play. So this sequence of models is meant to mimic homework 5 in terms of what it's going to look like practically speaking. We'll start with an empty model. So predicting graduate school ratings, performance ratings is my outcome. Empty model has nothing but an intercept in it. So if I don't know anything else about a person, my best guess for their graduate school rating is going to be the mean, because the mean is the most likely guess. That's what it means. So if I had outputs say that my residual variance is 200, I know that that is as much variance as this outcome could possibly have. I haven't explained any of it. In other words, I have an R-square of 0. Everything's still there. Let's say that I add predictor A, and I find that my residual variance goes down to 180. The R-square that goes with that, it's 1 minus what it is over what it was. So the R-square that shows up on your output is not calculated exactly this way. It's calculated using the sums of squares that went into the residual variance to keep it positive, but this is going to be close enough for government work, so to speak. And at more advanced models that I teach, multi-level models where there's more than one kind of variance that you're keeping track of, this is how we do it. So what this would mean is that I have an R-square of 10%. So my variance was 200. Let's say it went down to 180. That's a 10% reduction. Okay, with me so far? All right. Now, that also means that the change in R-square relative to the previous model is 10%, because we're going from 0 to 10%. That is a change in 10%. That also means that the semi-partial R-square for how much of the R-square is due to the new predictor is 10%, because the only thing that I added relative to the empty model is a slope for predictor A. So the slope for predictor A has to be responsible for the 10% of variance that has been reduced relative to the previous model. There's no other choice. So this is a situation in which you don't need a model. The correlation between A and Y squared would give you the R square, which would give you all this stuff. Okay, with me so far? All right. So then I ask you, okay, I want you to add the effects of GRE verbal, say, and GRE quantitative to the model. So we'll call those predictors B and C. And let's say hypothetically that your residual variance has gone down to 140. So now, relative to the 200 you started with, you have a reduction of 30%. 30% of all the original variability in this outcome has been captured by predictors A, B, and C as a set. So these two numbers are going to show up immediately on your output. You don't have to do anything special to get them. This number out here is the one that I'm asking you to calculate by hand, just like I did. The change in the R-square between models you can get by subtracting one from the other. It was 10%, now it's 30%. That's a change of 20%. Another way of looking at this same change in R square is as the semi-partial correlation squared for B and C. So if you have a nested set of models like this, you've added B and C, that's what makes them different. The amount of the R square that is attributable to those new predictors B and C is the change in the R square relative to the previous model. So we had a 10% R square, now it's 30%, and that's a change of 20. So this number right here, this column D, this is what I'm asking you to calculate by hand. Yes, there is a way that you could probably get the program to do it, but the way that you can do it is inconsistent across SAS and Stata. So I'm trying to make it fair. And also because when people approach these sorts of models in research, they often do this sort of hierarchical structure where they look at something, see if it matters, add something else, see if that matters. And so I'm mimicking what was frequently done in life. Now, yeah, go ahead.
Question, please.
Mhm.
So I was able to calculate the change, but when I look at the test statistic, then I try to do it the same way, but it doesn't work. So I was wondering how when it changes, I guess the F, the test statistic change is not the same as the R square.
Correct. And that was actually what I was going to say next. So thank you for setting up a beautiful pivot. Couldn't have been more better. Okay, yeah. So significance tests, right? I don't have any p-values anywhere on the spreadsheet yet. So this column right here, the model R square, that is given to you. The F that shows up next to it for your model is the significance test of whether that R square is greater than 0. It's the F for the model sums of squares, all of it put together. So at this stage, for instance, the F that goes with this 30% R square is the joint test of A, B, and C, because that's what my model has in it. The new thing I'm asking you to do in this homework is to get an F for this column. What is the change in R square? What is the increment that is due to adding the new predictors? If you add one predictor at a time, you don't need to do this because the t-test statistic for that new predictor is the test of whether the R square went up. So in the same way that the t-test statistic for the effective A gives you the F for the R square. T squared is F. If you're just adding one thing, then you don't have to ask for an extra test of whether that one thing matters because you get it already as the slope test. But in this situation, I've added two things. So I need to test whether or not those two things working together significantly increase my R square. I can't just look at the test of each because what they have in common also counts, but they don't get credit for it. So what could happen actually is that you could put B and C in the model and have neither of them be significant and yet still have a significant increase in R square. That would be like if B and C had concentric circles that were almost completely overlapping. Then neither of them would get credit for the overlap. Neither of them would be significant uniquely, but the overlap still contributes to R square. So to answer your question, to get an F test that goes with this change in R square, we need to write a statement that asks about the joint contribution of just B and C. And that is a contrast statement in SAS, where you would write B1, C1, or that is a test statement in Stata, where you would write B equals 0 in parentheses and C equals 0 in parentheses. And then you would get an F that corresponds to the change in R square that resulted from adding predictors B and C to the model. And the same thing would be true at the last step, where you're adding two more predictors. Let's say that the residual variance is all the way down to 80. That is a 60% reduction relative to the first model, the empty model, and that is a change of 30% relative to the previous model. So we would need to do an F test for this change that would have just D and E mentioned in it using contrast in SAS or using test in Stata. Okay, that's the new thing on your homework. Everything else you've done. Now, does that help, Jay? Good?
Yeah, no, it makes, I think I set it up incorrectly.
Okay.
That was the problem, like now that I'm looking at it. But the other question I had was that my intercept,
Mm-hmm.
you know, I thought so now that I've recentered three different things and my intercept didn't come out correctly. So I'm wondering, how do I troubleshoot to find out which intercept is not centered properly? Because it could be any of the three. Right?
If when you add the first predictor, if that intercept is right, then that predictor is centered correctly.
Oh yeah, that's so it's one or the
It's one
two.
of the new ones. Mm-hmm.
Okay.
Yeah,
Right.
and one is centered at 500 and one is centered at 550. Just
Yeah.
recheck your code to make sure that you haven't somehow mixed the two up, and that it's new predictor equals old predictor minus centering constant in each.
And then, oh, sorry. So one other question I had also is that when you asked after you add the two new predictors, you asked for like how does the degrees of freedom change?
Mm-hmm.
So when you look at the bottom one, the denominator,
Mm-hmm.
that shouldn't change, right? I mean, it's still the 199, and then you just subtract the fixed effects of the three, like the top three, or do you add also the effects of adding the combination of the two?
So the math is done for you. If you had 200 people in your data set, then your denominator degrees of freedom, the the total would be 199.
Right.
What it is in a particular model depends on how many predictors that you've added.
Right. And then you just subtract that. But that's okay. I must just be doing something wrong.
So
Okay.
like at this stage, it would be 198,
Right.
and then it would be 196, and then
Yeah.
it would be 194.
Yeah. Somehow. Okay. Yeah. I have to look at it again. It's not coming out right. And I don't know what I'm subtracting incorrectly, but
Well, you don't have to do the subtraction. It should be doing it for you.
yeah, so that's what I don't understand. Like, if the numerator is right, the denominator should be correct too. But somehow, yeah, I don't know. Okay.
Okay, make sure you're looking at the residual or error line and not the total line. Because numerator plus denominator equals total. Because numerator is what you're using, denominator is what's left over, and then total should be the combination of the two. Yep. And numerator for your f-test is always the number of slopes that you've combined. So like the numerator for the f-test for the model at this stage would be 5 because there's 5 slopes. But the numerator for the f-test that goes with just whether or not d and e added to the r square that goes with this over here, that would be 2 because it's just d and e that's being tested. But the denominator would be the same because it's the same model that you're pulling all this stuff out of. Okay, other questions on this? So this approach of adding things one at a time, although very common, is subject to someone arguing with you that you added them in the incorrect order. Right? Like someone may come along and be like, wait a minute, D and E are the most important things in my research. Why did you stick them in last? They should have been there and there the whole time. And to some extent, they have a point, right? The contribution of the change in R square depends on what's already there. So to avoid those sorts of ambiguities in how you added things and looked at the change in R square, that's the reason why in example 4, or no, example 5a that's based on example 4, that's what I meant, I have just one model that has everything in it. And then you can calculate using the same f-tests. You can ask for effect sizes that carve these things up into any way you want. And so that way you're not putting anything, you're not making any predictor have priority over another. You're looking at the joint model where they're all fighting against each other for what's unique versus what's common. And you can get the contribution to the R square arising from any combination of what's there. And so that's where the contrasts in, let me pull this up, find where I'm at. Yes, so this is example 5a that we started looking at last time. The model has everything in it that I would eventually want to add rather than adding things in piece by piece. And the nice thing about SAS is that when you write these contrasts, so these are examples of pulling apart the model. What's the contribution of A and B? What's the contribution of D and E? The first one on here, this is page 3 of example 5a. The first one demonstrates how you would go about getting the f-test for the model. That gives you the full R square. This is just a demonstration. It's not something you typically need to ask for. This one gives me the effect of the 2 slopes that describe my 3 groups. This one gives me the 2 slopes for age, and this one gives me the 3 slopes that make up education. And not only does it give you an f-test that goes with each of those groupings. So for instance, here's my contrast, my table that results from those statements. It gives me the F value. This is degrees of freedom for the numerator, by the way. It's the number of slopes that contribute to each of these tests. And each of these tells me whether the slopes work together to significantly account for variance. That's what the F is telling me is their joint contribution. And SAS also spits out this separate table that Stata does not. So this is total variation accounted for. There's more tables than that on the output, but I've limited it to just the ones that we're going to look at. This column here, semi-partial eta square, that is the amount of the R square that is attributable to each set of predictors that you lump together with the contrast. So the first one is for the model. All 7 predictors as a whole create an R square for the model that's 0.288. And so 4% was due to working class, about 8% was due to age, and 8% was due to education. And if I take these numbers and sum them, I get to about 20%, which is not 28%, because common is still out there. So what's common across these things is still contributing to the R square. This is what Stata doesn't do directly. The way that you would get these semi-partial eta squares in Stata demonstrated in that section of the handout. It requires you to estimate a model that does not have the term you're trying to get the semi-partial correlation squared for, to get the sums of squares for the model of what it would be without that, and then compute semi-partial correlation squared as whatever the sums of squares is for that term divided by the total. And so I end up with the same numbers as what I got in SAS directly. I just had to do the extra work to get it. So that's why I'm having you do it hierarchically in your homework. That way everybody has to do the same amount of work. Because I thought that was fair. All right, where are we at? 118. How we doing? Yeah, still here. Maybe my standard shouldn't be whether or not you look happy to be here and whether you're just still here, right? Because that's a compliment. The week before Thanksgiving, the fact that you're still here when you know you don't have to be, because I'm recording it anyway, thank you. It's all about perspective. So we've talked about, I think, this handout pretty much to death. The one thing that we haven't looked at is how the results compare. So I made a table on the very last section here that compares what the results look like for each of the predictors in their own separate model versus what it looks like after you combine them. And so each predictor, like working class, used to account for an R square of 10%, but after we controlled for age and education, its contribution for working class went down to 4%. So 10% versus 4% is because how people reported themselves as low, middle, or upper class is correlated with their age and education level. So the contribution of group is less after we control for age and education. And the same is true. Age used to account for 11% of the variance when it was all by itself. Now in the combined model, its contribution is down to 8%. Because age is correlated with education and self-reported working class in this sample as well. If we look at the parameter estimates, we see differences in most of these effects that make them smaller. So the unique effect of each predictor as given by its slope is reduced when it's in a model with other predictors. What it has in common, each predictor is not given credit for. So I actually computed the difference down here just to show you the effect of this idea of collinearity, that predictors are correlated, and so it's harder to find their unique contributions when they're more correlated, but their unique contribution is usually going to be less than what it would be bivariately, but not always. And then, as always, words. All right, questions on this?
Lisa, can you please go back to that Excel file where you had semi-partial R squared and R squared with A plus B plus C groups? Yeah, this one.
Okay.
Can you explain what semi-partial R squared means as it relates to, um, so for example, in uh, row number 3 and 4, like,
hmm
right, as we add B plus C, how does semi-partial R squared relate to this new addition? I remember you said something about the combined effect of B and C, but I didn't quite catch that.
Sure. Another way of, so the definition of semi-partial R squared, it's an effect size. It expresses the amount of the R square that is due to that predictor specifically. So like how many rooms did B clean and how many rooms did C clean? Like that contribution of those two predictors is the semi-partial R square. It works out if you're adding predictors in this hierarchical fashion like this, that the change in R square between models, so the model that doesn't have B and C versus the model that does, the change in R square of that 20%, that is the semi-partial R square for those two new predictors. It's what they brought to the table that wasn't there before. Because the total R square is up to
Okay,
30% relative to the 10 that it was before.
got it. Um, so semi-partial R squared would tell us the unique contribution whatever we add to the model makes, whether it's one predictor or a couple of them, like whatever the new stuff, the contribution that makes.
Yes.
Okay, thank you.
Yep. So we can always calculate this if we add predictors in this hierarchical fashion. What we then have to ask for is the f-test for the new set of predictors and their contribution. And that's the new thing. That's what contrast and test are for. Okay, other questions? Then I think what I want to do is finish out lecture 5 that describes sort of things that can happen in regression more generally. And I want to make a separate video that goes over example 5b, because example 5b is designed to be like a broader review of all the stuff that we've talked about. So that may be something that some of you may not need to watch or want to watch and others do. So that way we can talk about new stuff in class, and then I'll make a recording for that one that you can watch as much of as would be helpful. How does that sound? All right. So Venn diagrams. So effect sizes in these models. I like semi-partial R square. Even though you have to do a little bit of work to get it, it's intuitive in that it's like how much credit does each variable get as expressed in the metric of R square. There's also standardized slopes that you can report. This is easier to get in that you can ask your software to spit them out. That's the comma beta option of Stata, and it's also you can get it in ProcReg and SAS. However, they don't generalize well to interaction terms, and they are not as intuitive when it comes to grouping variables. So I prefer semi-partial R square, even though it's a little bit harder to get at, and it also generalizes to more advanced models that standardized slopes tend not to. But they're both valid ways of getting an effect size. All right, we were talking about assumptions. I think this is the new stuff. So let's pick up on slide 22 of lecture 5. So just a reminder, something that reviewer 3 may ask you about, and something that you should probably be thinking about ahead of any time. There's good news and bad news with all the stuff that you're learning. The good news is that you can think of these as building blocks. So how to put predictors in a model, how to talk about what they mean, how to describe their effect size and test their significance. These are skills that translate into almost any kind of statistical model. That's the good news. The bad news is that the samples of data that most of you are likely to be working with may need a different kind of model to be able to use these techniques accurately. So the general linear model is designed for situations in which you have a quantitative outcome whose residuals are supposed to be normally distributed. So there's a lot of kinds of variables that you might want to predict as outcomes whose residuals aren't going to be normal. And that's where the world of generalized linear models comes in. The other thing, the big deal, I would say the worst one that you could violate is independence. So if your people come to you in some sort of naturally formed group, like you have multiple kids sampled from multiple families, or multiple kids from multiple schools, or multiple teachers from multiple schools, like anything like that, the people who are part of the same group, their residuals are likely to be more related to each other than people who are part of different groups. And that screws up your standard errors, and it also screws up some of your the slope estimates. So that's what the world of multi-level models, or what's known as mixed effects models, are for. Those are the upper level classes that I teach for those situations. What ends up happening in those models is that you have to have built into the model a different type of E for every dimension that you've sampled over. So like if you were collecting data from schools and you had children from different classrooms, so the differences between classrooms would have like its own E for why some classes do better than others. And within a classroom, children would have their own E for why some kids do better than other kids from the same class. So there'd be two different kinds of variability that the model's trying to predict simultaneously, and that builds in a correlation of the residuals from people from the same group. So if you're in that situation, you cannot use these models as I've described them. You got to add stuff to it. But the techniques you're learning directly translate. Once you get the multiple E's set up, everything else translates very much the same. The other part of it that goes along with normality is constant variance. And so generalized linear models that have different types of outcome variables built into them have solutions for non-constant variance as well. So just sort of the caveat that GLM is not a one-stop shop for everything, but the idea of how you put predictors in is general. It does work beyond that. And other things that people may point out in terms of things we're assuming. All of our observed variables, we're assuming are measured without error. We may calculate a reliability coefficient for, say, a sum score or something like that, but we don't do anything about it. We would be like, my measure of this characteristic for my people has an alpha coefficient for reliability of 0.8. Ta-da! And I move on to stick it in the model. The idea that you may want to combine multiple sources of information and extract what is common across them to better represent a construct, a variable, that's the basis of what's known as structural equation modeling. That's the course that I teach after this one right now, and it's coming back next fall. So those models are designed to better address the measurement error that would occur in any one observed variable that we're ignoring here. We're also assuming that all predictors have their effects specified correctly. So we're assuming that a predictor has a linear effect if that's all the kind of slope you put in. We're assuming it has a quadratic effect if that's the kind of slope you put in. And so we can test that by adding other terms that would change the slope or the type of slope and see if they help the model. And anything you haven't included is assumed to be zero. That's always the case. And if you haven't measured it, then you can't do anything about it. So these are just some caveats. Here are some things that you may hear about from picky reviewers that are not actually problems. Multi-collinearity. Have you heard this term before? Yeah, it's spelled different ways. I'm not even sure which is correct. I love that the face is like, what? Either collinearity with one L or two L's or multi-collinearity. All of those words mean the same thing. It's someone who is concerned about the extent to which your predictors are correlated. They're very concerned about that. So you may see statistics given in output for general linear modeling programs that give things like tolerance, which is the amount of variance in the predictor that is unique to the predictor, or variance inflation factor, which is a ratio of tolerance. This is not a thing. So I would recommend that in your response to reviews, I wouldn't quote Lisa Hoffman, personal communication, this is not a thing. They will not be swayed by that argument. But what you can say is that, yeah, if you have predictors that are highly related to each other, their standard errors will be higher because it's harder to pin down what is unique if they're completely overlapping. Doesn't mean you can't try, it just means that that's the reality of the predictors that you've included. The only instance in which it is truly a problem, and you will know because you will get dots where your slope is supposed to be on your output, is a condition known as singularity, and that is when you have predictors that are perfectly correlated or are linearly dependent. So for instance, if you have a measure that has 3 subscales, and you put in each of the 3 subscales as a predictor in your model, and then you compute a total of the 3, and you add that as a 4th predictor, you will break your model because the 4th is the same thing as the other 3. That's singularity. So as long as you don't do that, you're okay. People. Another troubleshooting / investigative thing that you may be asked to look at is leverage. The idea that certain people, based on their values of the predictors or the outcome, have more influence on the regression line. So here's a picture that is illustrating each of these different terminologies. So if a case, a person, has has an extreme value of E, so like cases A and C, relative to everybody else, they're further off the line. We would call that distance. Leverage is cases that have extreme values on the predictor, like B, who's up here. And influence is the big one. That's cases that have an undue influence on the slope. So like person C out here, if they weren't here, the slope would be more positive, like they're dragging the line down. Whereas like person B is an outlier. They look like they're away from the distribution, but the line was already heading out there anyway. So B isn't having undue influence on the slope. It's the combination of where you are on X and Y that matters. You may ask for, as part of your output, a diagnostic for each case as to how much undue influence they have, such as a statistic known as Cook's D, which gives you how far different the slope would be without that case. So it's easy to find, to look at a scatter plot in this instance or to compute these things and see people who look like they're having a stronger effect on the slope solution than other people. The question is what to do about it. So some people might say, well, C looks like they have extreme influence. Let's get rid of them. Do you think I should be allowed to just kick people out of my data set? It's like, well, I want my slope to be more this way, so you're gone, and you're gone, and you're gone. It's like, no, it's not tailoring, right? You don't get to like nip and tuck your data until it fits perfectly the way that you want it to. Like, that is not cool. Now, the question would be, why is C like that? Do they give you some indication that their data is untrustworthy? Right? Do they have, say, a response time for a task that should have taken 3 seconds that took 10 minutes, like they're not paying attention? Or did they report that they smoke 18,000 cigarettes a day? Right? Like something to where it's like, okay, I don't believe you, and that's why you're not going to be in my model. But your value is inconvenient for me is not a good reason to kick someone out. And so it's hard to come up with a standard for what is too much that would allow you to kick out cases when someone else could look at the same set of data and come to a different conclusion as to where the line should be drawn as to who gets kicked out and who doesn't. So this is so-called outlier analysis. I would encourage you not to go down the road of kicking people out of your data. It's hard to justify where the line should be. Instead, you can switch models. So there is a technique that I teach in the generalized class that's known as quantile regression. So do you remember all the way back to like week 1 in this class and we talked about measures of central tendency? Remember that? Ever since then, that has fallen off the planet, right? We're all about the mean and the variance. But there was another one that we used to indicate central tendency that also started with an M. There were actually 2 more. Do you remember those? The 50th percentile? Yeah, median and mode. Yeah, well, mode is gone too, by the way. Mode has left the building. Mode is canceled for the rest of the semester, but median. So what if instead of predicting the mean for each person, we predicted the median? That's the basis of what's known as quantile regression. And the median is much less susceptible to outliers and skewness and all that stuff. And actually, you can predict any quantile that you want to. You can predict the 25th percentile or the 75th or whatever. So there are techniques that are more robust to outliers that work the exact same way. Under the hood, the difference between what quantile regression does and what this does is rather than minimizing the squared sum of residuals, it minimizes the absolute value of residuals. So it's a different optimization, but it's based on kind of the same ideas. There's not handy dandy formulas for standard errors. You have to do it via resampling techniques, but that nowadays computers do that within a second or two. So if you're in a situation in which you have randos that are messing with your slopes, right, and you're not sure whether you should kick them out or not, I would do a quantile regression instead to address that problem.
Lisa?
Yeah, go ahead.
Can you go back?
Sure.
So when you're looking at these like weird cases, is that something that like you like look at the plot and like try and be like, this like C looks really far out, B looks really far out, or like is there a more systemic way to be like, this person is an outlier?
I would ask the systemic way would be to ask the program to calculate the Cook's D or something like it for each individual case.
So you just like iterative run every single case?
No, it does it. It calculates this for you. It would be an option somewhere in the code for the model to ask it to add this additional column to your data set, and then you would run descriptive statistics and sort of look to see if there's any people who have a lot bigger D value than other people.
Okay, so Cook's D, it essentially runs it for each participant then?
It runs it without each participant to see how different the results would be.
Yeah. Right.
So
that makes sense.
Yeah, okay. It's an index of how much you're dragging the line, right? Because any one person shouldn't be able to drag the line more than other people.
Perfect. Thank you.
Yep. And ideally, no one's dragging the line, and you're fine. In reality, no, there's always going to be one or two people, and it's like, well, do I kick out just this person or both of these people? And then it becomes, so.
Mm-hmm.
Yeah.
Perfect. Thank you.
Technical term. Yeah. Okay. Suppression. We talked about that earlier. Suppression is a condition in which the unique effect of a variable is actually stronger than their bivariate effect. Yes, it can happen. Here are the situations in which it can happen. Given that there is a bivariate effect of 2 predictors, then if this mathematical equation is true, this one or this one, and number C is an example of what I have here below. So it looks like the predictors have a stronger relationship when they're combined in the same model than it looked like they had previously. And that can happen if they have a negative correlation. It's not something to worry about, it just looks surprising. There's nothing you can do about it, doesn't mean you screwed anything up. But what it does mean is that if you have a predictor that is not correlated in the first place, doesn't mean it isn't going to be part of your model. A bivariate relationship is not a gatekeeper for inclusion because this kind of weird shit can happen. Other weird shit that can happen. So this is an example in which, so here's a correlation table. This is SPSS output, by the way, that I borrowed from Cal Garvin at the University of Nebraska to make this point. Here is Y, and the first column here is the correlation of 5 different predictors. None of them is significantly correlated with Y. Nevertheless, if you put them in the same model at the same time, the model actually is significant. So again, making the point, just because something's not related by itself doesn't tell you necessarily what's going to happen when you put it together with other things. This is more likely to happen when the predictors don't have much correlation, and so each of them gets a strong, unique contribution. Here is an example of what's called null washout. So if I have one predictor here that's related to Y and none of the others are, and I dump them all in the same model, this model is not significant. Even though it has one predictor that is significant, the rest of these crappy predictors are dragging it down. Because your F test is a test of information that you have over information left over, but it's per slope. So if I have one good slope and 8 crappy slopes, then my per slope contribution is being dragged down by the 8 crappy ones. So it looks like the model is no good, even though there is a significant predictor in it. So the test of the model is not necessarily the only thing you should be paying attention to. It's what does each predictor contribute. And so that's the summary, the end of the story here, which is perfect because we have 2 minutes left. And this is the point where I say, do you have any questions? No, really. Do you have any questions? No, we're good. We're like, no, I'm done, Lisa. You say bye-bye now. I want to go. Okay, I say bye-bye now. Please, guys, stay inside, stay safe. It is dangerous out there. Let me know if you need anything, and I will see you after Thanksgiving, unless you want to come hang out with me during office hours on Tuesday. So if anybody wants help with homework or to review anything, 12:30 to 4:45 on Tuesday. Otherwise, see you in like a week and a half. All right.